welcome for everybody that's here. Obviously, we're speaking casually. Brian, Paulina, and I, the presenters, we teach together at the County College of Morris. I'm Kerry Flanagan, and I teach chemistry, introductory and organic, also instrumentation. So, would you like to introduce yourselves?
So I'm Brian Olson. I teach forensic science.
I'm Paulina Cardesi. I teach predominantly in biology, mainly anatomy and physiology 1 and 2.
I'm Brian Devitte. I'm a retired technology professional, but I do have a degree in biology, and I'm currently a STEM instructor teaching introduction to computer science courses at Bucks County Community College.
Okay. All right. I guess how we structured this talk, we have clips of ourselves instead of a PowerPoint. We actually have some videos of using Nano. So you'll see in Nano, it is a virtual reality software, and I have my headset here. This is how we met to film these videos. So Brian was our camera operator, Paulina and I were the ones doing the talking. So you'll see we were literally, as we are now, in 3 different locations, all meeting in a virtual room with our headsets on and working on a protein structure with a drug bound. So just to show you here, in case you never used one, you also have the controllers. So when we say our hands, we're actually using these as our controllers to work on the protein. So with that said, we have 4 clips that we want to show. So why don't we start with clip 1 and just jump into it because it is quite a powerful software for protein visualization.
Okay, so what we've done here is we've pulled up SARS CoV-2 main. We have taken a picture from the website that he has on GitHub. We imported it here into Nano, and once we have it imported into Nano, we can load it here, and you see it in your center, and from there you can do some manipulations, you can view it. Paulina will walk you through some of the different capabilities of how we can view this protein. So,
actually, let's do it. So what you can see here is our main protease that we've been working with and some of the capabilities that we're really going to be working with here in Nano. So you can see with my virtual hands, I can really very easily manipulate our protease here and really shrink it down to appreciate its size and overall structure and really bring it up to hone in on specific regions that I am interested in. So again, just to recap, we have our protease here with our ligand here in our active site, and you can get an appreciation of the 3-dimensional structure here of our protease. So let's go ahead and look at some of those characteristics. I'm just going to bring it down a little bit. From this view, we're able to get an appreciation of our secondary level of organization. Let's look and examine some of the capabilities that we can do here in Nano.
So Paulina just highlighted the structure. She's going to change what she's doing.
So what I'm going to show you in just a moment is now we're able to look at the 3-dimensional. So we're able to look at the surface area here of this protein and how it fills space. So this gives you a really nice appreciation of what this protease looks like in space. You're still able to get an appreciation of the atoms based on their different coloration in Nano, and you're also able to see and get an appreciation of our ligand here in its active site, all things we're going to discuss in further detail. So this gives you an idea of, again, how it fills space, and it gives you a lot of texture information about our molecule. Now let's look at it in a different view. So what we've done here is we've now hidden that 3-dimensional arrangement. So now what we're looking at here is this gives you a more complex look at this molecule and all the bonds going on within this molecule. So it gives you an idea of the atomic nature here of our protease. So what we're able to see here are all the bonds here between our atoms, which we're going to discuss in more detail in just a moment. And you're also able to see how they interact with each other. Now, let's play around with our ligand, because you'll see here in our model that you've kind of lost an appreciation for the ligand a little bit. So let's make that pop out some more. So some of the things that I can do is do a space-filling molecule. What I've done now is made that ligand fill up its space there in the active site. So you're really going to see how it occupies its space there in the molecule. So you still get an appreciation of the atomic nature here of our protease, but what the ligand is doing there. Now, something else that you could do here is you can also hide it. So let's say you want to remove that so you can examine the active site environment in more detail. You can actually remove that ligand from view. Okay. Let's explore some other things that we can do here. So here again, we have our ball and stick representation that gives you a great idea of what's going on with the atomic nature. Now let's look at how, if we want to see how this molecule fills space, we can do a van der Waals view here. So this shows how those same molecules fill space. So not as much of an examination as we saw in the surface area investigation, but you're still seeing how these atomic particles fill up space in our protease. All right, what else can we do? Now this we're familiar with. This is where we started, but you can see here what we did is we took that appreciation of the atomic nature and the bonds between our atoms, and we just filled in the secondary structure. So this is what we looked at before with our alpha helices and our beta sheets and our coils here and how they interact with the ligand. Perfect. This is what we looked at here. Now, what else can we do with this? We can do this arrangement, which is called a putty view, in which we took away that three-dimensional look of our secondary structure. Notice how the alpha helices here are going to be more two-dimensional in view here. So we took away some of that three-dimensional viewing capability there. Notice here how these yellow coils now represent our beta-pleated sheets. We still know what they are. Absolutely, but we've taken away some of that three-dimensional structure in order to focus on other things. All right. Let's see. Now, something that we can do as well is we can do what's called a wire view. What we did here side. So let's focus more on the ligand here, but keep the protein in mind. So what we can do is de-emphasize here the structure of our protein, but still keeping it in view by doing this wire view. Again, we have our ligand right in its active site, but we still get an appreciation of how it reacts with the rest of the protease without being distracted by more three-dimensional structures.
That's it for the one?
Yeah. So you can see there's a lot of different views in Nanome, how you can visualize molecules, proteins, whatever it is you're viewing. And yes, we're working with SARS-CoV-2 protease, but you can upload any protein that's in the protein database and look at it, visualize it. You can start building off of molecules and play with it. So yes, that's the one protein we're working with, but it's not obviously restricted to that. But it's really neat because, as Paulina was discussing, you can see so many different views depending on what you're trying to achieve. So the next clip actually we're going to start focusing a little more on the ligand and how you can select specific regions within the molecule, not just the whole thing. And then you could start to see the interactions between the two.
Now, I'm going to show you some more about the atoms and protein structure itself with the ligand. We'll break it down to just a few amino acids so we can really get a good look here. But first, Paulina and I switch places. So we're going to do something very fun. Teleport. Are you ready?
I'm ready.
Right, let's go. All right, so we switched places. Okay, so now what I want to do with this is, let me turn a little bit. Now I want to change the view. Not that I don't like stick, but let me turn this off. Okay, so now I want to get just a quick view of where my ligand is before I do anything else. Okay, so here we are, our entire protein structure, back to ribbon. It's just visually appealing when it's in this view. And now we can see our ligand in here. So what I want to do now is I just want to look at a few amino acids at a time. I'm not going to be choosy about which ones I choose. So I'm going to go to this here, just select a part of the chain. All right, so let's just look at a few. And then I will just choose stick from, and then I'll go to ribbon. Actually, to hide the. Okay, so now I have just a few of my amino acids chosen. So notice I've hidden the rest of the protein. Now, here is my selection of amino acids that I chose up here. And here we go. So why did I do that? Well, first, what is this? This is the primary structure of the amino acid. What does that mean? Or the protein. What does that mean? It's the sequence of amino acids that make up the entire protein. So every single amino acid has 20 amino acids and it has a unique structure. And every protein is built based on its unique primary structure. That is the sequence of amino acids. What amino acid in what order, essentially. So now I just chose a few just to highlight what we can do with this. So I'm actually going to turn the ligand off for right now. See the amino acids. Now what we can see now is, and I can manipulate this however I like, this gives us a good view of the atoms and covalent bonds. So now we can see here, we have sulfur highlighted in yellow. That's the chosen color for sulfur. We have blue for nitrogen, red for oxygen, and gray for carbon. And what we can see here in this whole entire structure is we have a couple of different bonds going on. They're all covalent, but we have a lot of single bonds, meaning sharing only 2 electrons. We have, notice, a double bond here between carbon and oxygen. So that's sharing 4 electrons between that carbon and that oxygen. We don't have any triple bonds, but it's possible. And we have what we call an aromatic ring, or a benzene ring, phenyl group. We have here, notice, it's all carbon, 6-membered ring, alternating double single bonds. So again, that would be considered a nonpolar region. That will come into play later. So a nonpolar is, for us, our purposes, carbon and hydrogen. We don't see the hydrogens, but they are there. And then polar groups would be our, what we call here, an amide, where you have the double bonded oxygen with the carbon and nitrogen. So that would be an amide. We have one here, have one here. And we have another one here, here, here. Just have an amine, just a nitrogen hanging off here. And we actually have a double bonded nitrogen here. We have some nitrogens here. We have a nitrogen on the end there. That's pretty much it. actually one more, just one more for this particular amino acid sequence. We have an aldehyde here. So what's really neat about that is we can, if we are interested in a specific region of the protein, we can highlight just that specific region and look at it and see what kind of bonds are there, what kind of atoms. If I want to see more specifically with that, I can do ball and stick and notice what just happened. I did my whole protein. So I can bring it back anytime I like and bring the whole protein back. All right. This is actually, like we said earlier, a very cumbersome view, but now you can see the wide array of, I was just looking at a handful of amino acids. That's the protein structure, essentially. It's composed of amino acids. And now I can see all of them. But this is a really hard view to understand while I am looking at my ligand, per se. And I want to bring my ligand back, actually. And notice it's right here, highlighted right now so I can find it. And I will unhighlight it in a second. I just wanted to make sure I can see it, right? So even this, even just ball and stick, here's my ligand, and here's my entire protein in just stick. It's still even hard to see. So I'm actually going to, here's what Paulina was talking about earlier. Okay, if I want to study just the ligand, well, I'll just turn the protein onto wire where I can still see my atoms and my ligand together. Now I can study both. And let's start to talk about why I would want to do that. I want to actually start thinking about, we're going to get into ligand binding later, and why do I possibly want to see my protein with my ligand? What am I looking for? I want to see any kind of interactions. So notice I mentioned earlier polar groups within my protein. Well, I have polar groups, as you can see on my ligand. There's a term in chemistry that we use, like dissolves like, when you're trying to dissolve a solute into a solvent. The same kind of theory applies here, where nonpolar groups are going to interact with nonpolar groups via the same intermolecular forces. We call them van der Waals interactions when it's just strictly nonpolar. So carbon and hydrogen, essentially, for our purposes. And when you're moving into other groups, polar groups, the oxygen, the nitrogen, even the sulfur, we start to get what we call polarity. That has to do with electrons, and is it more electronegative, meaning having non-bonded electrons or unbonded pairs? That's where we start to see interactions with polar groups. It makes poles, what we would call unequal sharing of electrons. So then if we have a polar groups, let's say right here where I'm looking, we have a nitrogen and an oxygen, that possibly can interact with this oxygen and nitrogen on my protein right here, if it's close enough. I don't know if it's close enough. I'd have to do some measurements, but that's something to test and see. And let's see, on this side, come back over here. I'm looking at my oxygen here. Is it hydrogen bonding here with this nitrogen? That's a possibility. Or this one down here, I have this nitrogen oxygen. Is it interacting with something down here? I see this ring structure on my protein. That's a possibility for a hydrogen bond right there, or at least a dipole-dipole between two polar groups. So that's something interesting that we can start to see. And maybe we do want to go back, what Paulina was showing us earlier. Maybe we want to go back to our ribbon structure and see our cartoon, but the atoms, let's hide all of that. And maybe we do want to look at the, actually, let me hide that, just kidding. Let me hide the ribbon. I want to show you surface. So maybe we can see that surface a bit better if it'll load for me. Sometimes it's a little delayed in loading. That has to do with a lot of calculations going on. So now I can start more thinking about that group that I was discussing earlier. So notice this polar group, maybe I could see it better with space fill. It's closer than you think. Maybe it looks like in ball and stick or wire or just plain stick. Actually, with the space fill, I can see it a little better. that is actually, notice the surface, what we would call the binding pocket. That fits quite well actually down here. This is sticking out a little bit, so maybe that's interacting, maybe it's not, but this is fitting quite well in this binding pocket.
That's it for the 2.
Okay. All right. So in our next clip, now that we have seen Nanome, how it works, how you're really able to manipulate and change that molecule to change your view, what we're going to do in our next clip is we want to focus on that binding pocket. So what we're going to do in our next clip is look at the linear, secondary, and tertiary structure of our protease and how we can then now manipulate that ligand in that binding pocket. So in that next one, we're working towards drug design and how we can start manipulating our ligand.
All right, so now that Carrie and I have and what's involved. So again, to recap, we have our oxygen shown as red. All right.
I'm sorry about that. Do I need to run that from the beginning?
You had the words there. At least I've got the caption, so I think, at least for me, it was okay. I was able to follow.
Okay. All right. Sounds good. I'll just put the volume back on. Sorry about that.
Shown as red, our nitrogen shown as blue. We have a sulfur over here in yellow, and our carbons bonded together. So this shows our amino acid linear sequence. This is going to be our simplest level of organization, and it's going to create this long linear chain of protein, of amino acids, pardon me. Now, these and how they come together are different groups, as Carrie was saying before, have some polarity. They're going to interact with each other. That interaction is going to dictate our secondary level of structure, our second level of organization, which are those alpha helices and our beta pleated sheets we showed before. So let's show those interactions. What I'm going to do here is go back to our protein. And now the whole protein is back. So this is perfect because it shows the amino acids we were looking at. So our amino acids of interest and that sequence, and how it's now going to relate to our secondary level of organization. So you're going to see here, we're going to zoom in just a little bit. You can see those same amino acids and now how they're going to start to interact with each other in the chain to create the secondary level of structure. So shown here, this is a perfect example. We're going to see a coil here of an alpha helice. So you're going to see how they're going to interact with each other to form this coil, an amino acid sequence, and how they're going to interact with each other. So now how does the whole thing interact? And that's going to be our tertiary level of structure. I'm going to bring back the surface. It's going to load for just a second. There we go. And now we get an appreciation of our tertiary level of organization. So still highlighted here in the middle is our original amino acid sequence. So you can see where we started and where we got to at our highest level of organization. So here you can get an appreciation of how all those individual amino acids arranged in that linear sequence are going to interact with each other in increasing ways to give us this overall complex structure with this complex topography, including our active site for our ligand. And that's going to determine why this ligand interacts within this binding site the way it does. And we're going to come back to that when we discuss the influence of water. So let's pick up with a discussion now of our ligand now in our active site. So we're going to keep our three-dimensional surface image on here, and I'm going to just pull this up a bit. I'm going to go ahead and just open this up a bit for you to see. So what we're going to see here is we have our ligand here within our active site, and you're going to see two amino acids highlighted. We're going to be focusing on those. This site here is going to be our cleavage site, which we're going to talk about in just a second. So what we're focusing on here is what the ligand is doing in here. So I'm going to just go ahead and remove our surface. And we're going to focus on this relationship shown here. Now first, before we get into this, we have to mention this is a protease. This is our SARS CoV-2 protease. What does it do? Cleaves protein. So here within our cleavage site, we're going to be focusing on these two residues. These two residues are going to be our catalytic residues. What they do, and I should mention them first, we have histidine highlighted here. Notice the ring. And we have cysteine over here. Notice the sulfur. They're going to be really doing the work of doing the catalytic work of doing cleavage. Now, what we're intending to do here, what is our focus, is if we can find some way to inhibit this region, we're going to inhibit protease activity and essentially kill this from doing any viral replication. This is our focus moving forward and what we can do to inhibit this area.
All right, so we have one more clip, and it's actually going to start getting into how do you start manipulating your drug or your ligand that's bound to the protein. So there is a chemistry builder within Nanomes. So you can build a molecule from scratch. You can import molecules and start building off of it. So either or, you could build them ahead of time, maybe in ChemDraw or something, and then import it. You can import databases. There's a lot you can do. So we had one particular ligand that we had imported with the protein structure that we were working with to demonstrate. But like I said, you can build your own or import a different one, many options. So this last clip will actually start getting into, well, how do I start designing and building off of a molecule? So take it away, Brian.
So the view we have here is just our binding pocket with our ligand, and you might notice one other change, which I'll address. So you can see our binding pocket, the protein, the gray and the red and the blue, that is the atoms of our binding pocket, our protein. And then in orange, we can see our ligand bound to it. Now, what we have here is also the surface that you can see, the surface of those atoms, the space they take up. Now, what we added to this structure now, you might see these little red spheres. And what they represent, they're clusters of water, where the water tends to congregate on this structure. Now, why would we care about that? I promised we would get to it at some point in the presentation. Why would we care about these waters? Well, what we're looking for are waters that are high energy and low entropy. And you might think, well, why? They're unfavorable. They don't actually want to be in that position where they're within the protein bound to it, where they have that high energy, low entropy. What we can do then, if that's the case, it would be in our favor to displace it, remove that energetically unfavorable water. How do we do that? Well, when we're thinking about our drug design, we have this ligand here. We can modify the structure, put a group on it that will be able to bind the protein and displace that water. That will be a more energetically favorable situation if we can displace an unfavorable water. Now, what we're thinking is we've identified one water that is energetically unfavorable, high energy, low entropy, and it is this water right here. So what we want to do is take this ring structure here and put a polar group on it that will interact with our protein and displace that water. That will create a stronger binding affinity for our drug molecule. And that's the goal. We want our drug molecule to be bound to this protein. Remember, we talked about inhibiting its function, and if we can get our drug bound to it more tightly, that'll help with inhibiting its function. So what we can do is then add to it, displace an unfavorable water, strengthening our attraction between drug molecule and protein. So we're going to go ahead and do that. We're going to change views, and then we are going to focus on that water, add a group, and displace it. And then we'll see what happens. All right, so now you can see the structure changed again a little bit. So cleared out all of the clusters of water except the one we are interested in, the water, and you can see it right there. So what I've pulled up, said we want to put a polar group on there, so I've pulled up my MedChem menu, and now I pulled up a hydroxyl or an alcohol group. And what I'm going to do is I'm going to put it on that ring and do what I said I would try to displace that water. So let's go ahead and do that. Let me highlight. I want to put it there. So, and you can see I made a connection. You can see that I've made here hydrogen bonding, but I can still see the water. I don't know if that means it got displaced or not, if the program will actually go ahead and do that. But you can definitely see I definitely made that hydrogen bond right there with the protein here. Very cool. Also looks like it's making a hydrogen bond here. Definitely put a group there that helps with interacting with the binding pocket for sure. Since in this view, it's a little difficult to tell, as I was saying, that if this water was displaced or not. So let's change views actually really fast, and let's look at space fill. Now looking at space fill, if I really look, it actually is taking up the same space of the water in here. Since it's taking up the same space, this new group here, this hydroxyl group, it is safe to say that the water is probably displaced. I wouldn't know for sure without experimentally determining that, but from this simulation, that's the point of this simulation, it is safe to say that because it's occupying the same space here, there is a good chance that that water was displaced. So answering that question.
So with that, we actually have a few small projects going on with students. Brian is the person who runs our virtual reality lab at CCM, and he onboarded me. And what I did last semester is I had an honor student who wanted a project, and he's still working on it a little bit this summer. We haven't quite been successful with it yet, but what we want to do with Nanome and this project in particular with those waters, they're actually different file types, and our goal eventually is to get those file types to talk to each other so nanome becomes more powerful. And that, notice I was talking about the water displacement. We want to be able to actually visualize that happening. As you make drugs and bind the molecule, you actually want to see that water displacement. So that's something down the line that we're trying to get going. But also, well, the title of our talk was gamification. So, well, how do we gamify this? How do we get students interested in this? And that's the other ongoing project right now, is making that happen. So now that we get students in there, get them to understand nanome and how to manipulate it, and that's where I come in this semester. So hopefully I'll have an update by the end of the fall semester on how this went. And I am using my organic one lab as, I hate to say guinea pigs, but they're going to do this for me, whether they realize it or not. And get them in the VR lab. Let them start playing with nanome, because I teach them ChemDraw, but now I want them to also add to that the virtual reality, the 3D. And this pulls in real world applications into their course. And they start to see this isn't just some random protein. We're actually working with SARS CoV-2. We're in the middle of a pandemic, and this is relevant. This is happening now. Yes, we're starting to come out the other side of the pandemic, but still, it's fresh in our minds. So this is real world application, because sometimes students say, well, how does what I'm learning relate? Perfect example. We might have students interested in drug design. So here you go. Here's a prime example. Now you can do real research. You might play with a molecule and discover something. So, and that's where the gamification comes in. Let's play a game. Let's break out into some groups and see who can design the most molecules, the most interactions, submit them. Dr. Olson, Brian, can run them through his simulator. He has more software that he works with, and do calculations and see, were we successful? So how many drug molecules did you submit today? And that's how we want to get them involved and start to play games, make it a little competition, see who can get the best interaction, who can get the most molecules. So that's one way to do it, at least where I see my course going with it. And having fun with Brian in his virtual reality lab, excuse to use it. But Brian and Paulina, do you want to add anything to that?
I would say that the real world application combined with that, like a healthy competition, is very impactful, particularly when you put the virtual reality headset on and you experience it firsthand. That's the thing about it, is it's an immersive experience, one in which it's, you know how you're with a friend and they're discussing someone from work, and they talk about them all the time, and you've heard everything and you know everything about them, but you don't really know them until the day you go to the lunch at work and you meet the person, and now the whole picture comes together. And even at that point, you start to be able to predict that person's behavior because you met them. So when your spouse talks about that coworker, you're like, oh yeah, that one. Well, this is what it's like when you go into VR and you see these things in a 3D space. It's like that recognition of a person that you've met, and you really get to know these proteins, and you really get to know these drug molecules in a way that it makes something highly familiar and important to you, so that when you go back to class, you have something to connect everything to, rather than spending the day talking about these invisible molecules that no one's ever seen. And so I think that it has an impact on the attitudes of the students coming into class as well. They come into class thinking that we've gone so far above and beyond in our attempts to make class interesting for them that the positive attitude bleeds over into everything else.
And what I found when I got into nanome, jumping off of what Brian's saying, is that immersive experience. We're looking at video clips, and they're on your computer screen as 2D. It's a completely different experience when you are literally sitting in the molecule all around you. You can make it as big, as small as you want and really see it. And if you have students who are like myself, kinesthetic learners, need that tactile, this really brings them in, because now they can sit there and really play with the molecule. And everybody does it the first time they're in it. You see them. you're trying to talk and they're just playing and looking at it and flipping it around and make it big, make it small. And it's funny because you know exactly what they're doing. They're actually playing with the molecule because they're so enthralled with it. Like, wow, look at this. And so it really does bring that, like I said, that tactile. If you're one who learns by doing and by feel, this is for you. So it really engages those students. And sometimes I do get students interested in like, wow, I never knew that. Or I hear you talk about in your lectures about drug design and how drugs were discovered, but this is something completely modern now and a technology that we can use that we can see in real time as you build molecules, how it interacts with a protein. And before, we just have softwares. You run calculations and you get numbers, great. But you were saying sometimes you can see visually, you have colleagues come back to you, and how did you figure that out? Well, you're looking at it in 3D, not 2D on the computer screen. So it's very useful in that.
And if everyone had VR headsets, we would be in a virtual room, all standing around, looking at the molecule ourselves, and you can even do 3D virtual tutorials. So, but it's 11:58. I think we have to wrap up.
We do. Does anybody have questions? Okay.
I have a question if you're able to hear me.
Sure, go ahead, Aisha.
Sure.
Hi, I'm Aisha Fields. I'm from Howard University, and I think this has been a really cool presentation. I like the idea, although we don't have it yet, a virtual reality lab, period. And so my question is, how can I follow up to ask more specific questions about how to get something like this going at our university?
I just put my email in the chat. B Olson, BOLSON @ccm.edu. You can email me because I know like the technical aspects of things and kind of like keep up with the way things are moving. And I'm happy to discuss all of that with you.
That would be fantastic, because that, of course, is the answer, the question that administration always has with technology. It's like, we invest all of this money into VR headsets. How long is that going to be good for us? I'm sure you've worked out all of those sort of kinks, and I'd love to talk more with you about how to navigate that. But thank you for the presentation.
And Aisha, if you get a virtual reality lab at your school, we could collaborate then, and no traveling. Everybody just put on a headset. We could all meet in the same
How cool
room.
would that be?
Yeah.
Open a room and all meet in the same room together.
Yeah.
That'd be amazing. Let's do it.
All right. We like to hear that.
Okay. All right. Thank you for the comment, Stan. Yeah, you make a great point about VR being so helpful in teaching the complex subjects, because it does kind of simplify things through the immediate perception. That software works on multiple different types of VR headsets. They have to be the higher end, something like Oculus or Vive. Whichever headsets run Nano, you can use. And that's NANOME. You can just check that out and get all the information.
Of course, they have a website if you wanted more information on Nano. What is it? Nanome.com.
Yeah, Nanome software.
Yeah. So they break it down on their website, everything you possibly want to know.
Thank you so much. You guys are great.
Thank you. Glad you came.